Hey, check it out. New personal best. This is my very first VCO circuit. Mostly my own design, but a lot of influence from a lot of things that I researched over the week. And man, this was challenging. What I came up with here is pretty cool. It's probably too cool for its own good. Let's turn it on and see what it sounds like. It's got the voltage controlled pitch here. It sounds like it's struggling, and that's because it is. I'm driving this little 2-inch speaker from an LM741. Not really designed to drive speakers directly. We're going to work on the sound a little bit, maybe in the coming week. But this is the cool feature. It changes how saw versus triangle it is. It's not supposed to change the pitch, but it does. It's a challenge, and it comes down to pairing again. So let's look at the circuit, and you'll understand some of the challenges that make simulation different from reality. Yeah, let's start over here with this diode bridge. This looks like a little bridge rectifier, but it's actually a really cool little switching circuit. I got this from W2AEW, who's a YouTuber who does some great electronics videos. This is number 104 of his, and I'll put a link to that in the description. But suffice to say, we have a couple of current sources coming in here, one coming in this way and one draining kind of out that way. And depending on what this square wave is doing, high or low, it basically switches between these two. I'll let him explain that if you want to look at that video, but it's super cool. That square wave is being generated by this oscillator here, which is controlled by this capacitor. So what's going to happen is we're either going to be charging the capacitor by shoving current in here, or we're going to, when this is high, it'll pull the current in this way, and when this is low, it'll pull the current back out that way, and it'll drain the capacitor. And when it will keep on charging until it reaches this threshold that's determined by this simple voltage divider here. So just 50% between the ground and the rail. And if this is high, then it pulls the threshold high, right? And if this is low, then it pulls the threshold low, right? And so that creates the hysteresis. Pretty cool, simple little thing. And so this is mostly that circuit that I'll link down below. How am I getting that current? Well, I have some control voltage. There it is. This is the VCO, or the VC, the voltage control part of the circuit. And I invert this so that I have both a positive voltage and a negative copy of it. And now these two resistors need to be the same value. If these are not the same value, then the positive and negative won't be exact opposites of each other. And you want those to be exact opposites so that the rate that it charges is the same as the rate that it discharges for a triangle wave. If those are slightly different, right, then as we kind of weigh those two differently, then we'll get it'll change in pitch as we change the amount of saw. So how do we change the amount of saw? This is the part of the circuit that I came up with. Basically what we do is we buffer that control voltage and that negative control voltage into this current source. And so we have, just like that mini Moog Model D circuit that we saw the first week, we create a current source by making sure that this matches that. And what's it going to match to? It's going to be, we're matching, yeah, so depending on how much, so we're matching the voltage. The voltage matches exactly, right? And then we can change how much resistance is here coming in from ground. Right? In this case, it's negative, so we're pushing it into ground. And so if this is a small amount of resistance, then we'll have a large amount of current coming through here, right? And if this is a high resistance, we'll have a small amount of current coming through here going to ground that it's mirroring. Okay, so that gives us the two sides of the triangle wave, and because it's a single potentiometer here, the sum of these two currents will always be the same. But these are referenced to ground, and so that means that this current will only ever be able to drive, if we were able to put the capacitor here, this current would only ever be able to drain it down to ground and charge it up to ground, right? And so we'd never be able to go, up past ground and then back down past ground. So what we need to do is we need to create a mirror. And so this is a simple way to make a mirror using an op-amp. And so we have, again, matched resistors here. What happens is because because we're pushing current up, we're pulling current down from this 12 volts, right? Pulling it down to ground through this. The voltage drop off over this, we want it to match the voltage drop over here, and we do that with negative feedback in this op-amp, right? And so this transistor will open up just enough to match the current going through these two resistors, because if the current is matched going through these two resistors, then the voltage will be matched, the drop across them. If these two resistors are off by, say, 5%, then the amount of current that we're driving through these two things will be different by 5%. And 5% might not sound like a lot, but it's actually quite a bit of pitch, quite a bit of pitch. But now what we've done is before we were referenced to ground, and now we're referenced to the top rail. Top rail minus whatever is here, and minus whatever drops across here, about 0.7 volts. And so that is basically what allows us to drive the inputs to this switch, right, which drive the capacitor. Now, I chose the LM648AIN because this is a rail-to-rail op-amp, which means that it can go all the way up to plus 12 and all the way down to minus 12. Unfortunately, this op-amp can't drive this much voltage. And so I was actually cooking this guy a little bit. So I swapped it out for this TS358CD, which can handle the voltage and more current than this little guy. But this is not a rail-to-rail op-amp. And so what ends up happening is that as this approaches the rail here, this positive rail, it can only raise this pin up to about 10 volts. 10.5 volts. It can't get all the way up to 12. And so that means that if I'm raising this to 10 volts or so, so if the drop across this is small, so if we have a small amount of current going through here, then this is not going to be able to do its job. And so let's hear what that sounds like. And so what we're talking about is if this here gets larger, we're going to be drawing a smaller amount of current through here, smaller amount of current through here, and smaller amount through that resistor up there. And so that's controlled by this potentiometer right here. So when I turn this potentiometer clockwise, we hear the pitch increase, more current, and when I turn this way, this is controlling the control voltage, the pitch decreases, and at some point it just clicks out. It can no longer it can't sustain that thresholding. It can't sustain the voltage mirror. So we can turn this back up. And the same thing will happen here. When we change the percentage that's on either side. So let's take a look at what that looks like. So here's the voltage across the capacitor. It's a little bit hard to see, isn't it? You can see the voltage across the capacitor. We see something like a triangle wave. And if I change this, that changes the amount that's on either side, we see it squishing together because the pitch is changing. But you see how it's leaning to the right a little bit now? And as I turn it this way, now it's definitely leaning to the left. Let's see if we can increase the resolution here a bit so you can see it better. Okay, leaning to the left. And leaning to the right. You see how we can kind of change those two independently? So that is the circuit that allows us to adjust how triangular or saw-like that wave is. And I think it's pretty cool. Obviously, there's a lot of work to do. One thing you may have noticed is that bridge rectifier that I need, usually it would be made out of diodes like this, or some dedicated bridge rectifier component. Unfortunately, I only have 2 diodes and I needed 4, so I used LEDs. And that could be part of the reason why it sounds so wonky. But I think this is a pretty cool milestone. First VCO, and I learned a lot, and the next one's going to be better.